All right, everyone. Gonna start pretty soon. I have a little bit of a cold, so my voice is a little funny, but I hope we can work past that. Yeah, I just haven't been feeling good, so I've been taking a little bit of a break, and I'm just not feeling well, so just wasn't up to streaming much the last couple weeks. But yeah, so we've been doing complex analysis, talking about holomorphic functions. So I'm just going to continue along that path. We have our book here, the book I've been following, Green and Krantz. So one complex variable. We're not going to get into any multivariable stuff, probably ever. I'm not an expert in that for sure. So. But the one variable stuff I'm pretty good with. We just got into Cauchy's theorem and Cauchy's integral theorem and Cauchy's integral formula. So let me just remind you of that. So we're going to talk about complex power series today, and the this Cauchy integral formula will be kind of important. So this is lesson 27, complex power series. Okay. Right. So let me just make sure this is lined up properly. All right. So I'll be looking at page 69 for now. Here we have a theorem, which is basically a generalization of the Cauchy's integral formula. So Cauchy's integral formula was when k equals 0 here. Or in other words, it was just for the regular function itself, not the kth derivative. So the generalized formula says that if we take k derivatives of f of z, we can write this also as an integral. It's k factorial over 2 pi I times this closed integral, where we take this circle of radius r around some point. And it's very similar to the other integral. So f of, this is like f xc or zeta actually. Right, just some other variable. So they like to use zeta. So it's f of zeta divided by zeta minus z to the k plus 1 power, and then d zeta. All right, and then here, of course, k can be 0, 1, 2, or any positive integer. Right, and this formula is very important. Again, when k equals 0, it's telling you that the value of the function at a point is sort of like an average of the values around of this function around this circle. So this is just a generalization of that. It's giving you an estimate, or not an estimate, it's actually equal for the kth derivative, again, as this sort of estimate or average. And this becomes important for estimates later. We get into Cauchy estimates, and you can estimate this integral because it has a finite length of the path. And if you can bound this function, you can end up getting bounds on the function or the derivatives of the function using this same formula. So let's specify what has to be true here to be able to use this. So let me just be careful. So this is true that the kth derivative of f can be written this way as long as the function is actually holomorphic inside this disk here. So really we want to say let u be open, u in the complex plane be open. And f is holomorphic. So sometimes, again, I'll write holomorphic on u like this. So f is holomorphic on u. So first, then f is c infinity on u. in particular, we know all the higher derivatives. They're given by this formula. So it's C infinity. In fact, we'll show in the next step, in the next theorem or lemma, that f is C infinity. Moreover, we need the disk to be contained in U. This disk that we're integrating, so the closed disk needs to be contained inside of U, and Z needs to be inside of this disk. So let me just write that. Right, so moreover, if this closure of this disk around P of radius R is contained inside U, and Z is inside this disk, same disk, but inside the interior, not the closure, then we can use this formula. Right, so just a couple things we need, but essentially you could think of being able to use this formula as long as the function, you know, is holomorphic, and it's holomorphic on the boundary of some closed disk. So maybe U is a little bit bigger than the closed disk, but definitely on the boundary, and everywhere on the inside, everywhere in here, F is holomorphic. If that's true, then we can use this generalized Cauchy formula. Okay. And what does the proof look like? Well, we didn't even do the proof for k equals 0 case, but essentially you're going to use the k equals 0 case and then prove a formula for the derivative using sort of like a trick. You can look in the book for the argument, but so you basically use the k equals 0 case and this little trick for the derivative to prove the k equals 1 case, and then you just use the same argument over and over again, and you kind of pick up this extra k factorial term. But essentially it's just the same argument. You just keep using the argument on the derivative, and then you use the argument on that derivative, and so you get a second derivative, and etc. Okay. Are there any questions in the audience about this theorem in general, or about we've talked about integrals in the past, but maybe it's been a month ago or so. So yeah, if anybody has any questions, let me know. Let me lower the brightness on here. Okay. All right, I don't see any questions. Okay, and then let's prove this corollary as well, that I'm not even sure if they prove that F is C infinity on here. Or sorry. Right. This proves that F is C infinity, and then the next corollary is about F. If F is holomorphic, then the derivative is also holomorphic, which this sort of hints at here, since we get like a Cauchy theorem for the derivative, right? But it's not clear that the derivative is actually holomorphic. So this next corollary just makes that more clear. And then we'll get to power series after this. So, but this Cauchy integral formula is very important for understanding complex holomorphic functions in general. Okay, so corollary 3.12. This says if F from U to C is holomorphic, then F prime is holomorphic. Right, so this is kind of a surprising result, because the way it's defined is the derivative, it's just like the normal derivative in the real case, except now you have complex numbers, right? Or at least, you know, earlier in the book, that's not the definition, but they show that it's equivalent to this limit definition, right? So in the real case, it's not always true that if you have a differentiable function and you take the derivative, that the derivative is also differentiable, right? Not every function is C infinity, as we would say. But for the holomorphic case, it actually is the case that if it's holomorphic, then the derivative is holomorphic. So it's sort of infinitely differentiable automatically. And that's a surprising result here. So use the fact that f is C infinity from the last result, right? So use that f is C infinity on U by the last result because it has all these infinite derivatives. So then obviously it's C2, so it's mixed partial derivatives. We need them to commute to be able to use this argument. So basically we want to show that by definition, the definition of holomorphic is that the derivative with respect to z bar is 0 for the function. So we want to show that dz bar for f prime, which also f prime is just the derivative with respect to z. So they go over this earlier in the book. So we want to show that this is 0. Hello, Kyler. Holographic or holomorphic friends. So yeah, this is the derivative of f here. It's just they show earlier in the book that you can think of the derivative of f as just being the partial derivative with respect to z. And we want to show that this function is holomorphic, so we want to show that its derivative with respect to z bar is 0. But because the function is C2, these two partial derivatives commute with each other. So that means that this is actually equal to the derivative in the other direction, where I do the z derivative first, or sorry, z derivative out here, and then z bar derivative inside. But because f is holomorphic, this z bar derivative is 0. So this is just equal to d dz of d dz bar of f of z. But this inside part is 0, so the derivative of any of 0 is just 0. So it really just has to do with this swapping, the fact that it's C2, and we know it's C2 because it has, in fact, infinitely many derivatives. Right, so if you want to know what's the derivative of f, you just take the derivative with respect to z. That gives you the derivative. And if you want to know the second derivative, you just take a second derivative. And you know that all the derivatives with respect to z bar are always 0 because of this same argument, basically. You can always commute these and put the z bar one first, and then that one's always 0 because f is holomorphic. And that's our definition of holomorphic. It's holomorphic if the derivative with respect to z bar is 0. Okay, or in other words, if you want to think of normal partial derivatives, you could just say we've just shown that f, the derivative of f also satisfies the Cauchy-Riemann equations, which is equivalent to this partial derivative with respect to z bar just equaling 0. Okay, right, so let's get into some power series. So this is 3.2 and 3.3. Any questions? So f holomorphic on U, then the derivative is also defined on U by definition, or not by definition maybe, but very close to the definition. And then f prime is defined on U, and we just showed that it's also holomorphic. Yeah, excuse my voice, but I always feel like holographic and holomorphic sound very similar, even though they have like nothing to do with each other. So this is 3.2 complex power series. And I don't want to say too much about this section other than it's very similar to the real case, which I also haven't talked about in any of these lessons either, but I'm sure a lot of you have seen power series before. It's probably easiest to just think of it as like an infinite polynomial. Hey, famished. So what would an infinite polynomial look like? Well, you have coefficients like a0 times 1 plus a1 times x, and this kind of just keeps going forever, times x squared, x cubed, right? Except that there's no end. Like a normal polynomial, all the AIs would eventually all be 0, but for complex power series, also we're going to allow these coefficients to be complex as well. So that's another difference from the real case. Let's just call this like f of x or something. Or maybe I should have used a z since we're dealing with, yeah, I'm a little sick. Sorry about the voice, but yeah, I'm getting over a cold. My head feels fine, but the voice is still messed up. So yeah, we're just talking about complex power series a little bit. Basically, you know, if you know the real case, it's very similar to that, but now we're allowing these coefficients to be complex. And just to remind you, for Taylor series, or maybe I'll just do the Laurent series, but so let's just assume P, the point we're doing the Taylor series around is just 0 for now, just to make things simple. But there's this notion of you know, taking a Taylor series expansion of a function if it has infinitely many derivatives. We can look at the coefficients, which are, this is in the real case, but the, you know, same type of thing applies here. We can think of these coefficients as the ith derivative at 0 divided by I factorial. Right? And then this gives us our Maclaurin series or Taylor series expansion around 0. Everybody's getting sick. Yeah, I don't know. I guess it's maybe allergies or something, but my mom got sick too, so I don't know. Everybody's sick, yeah. Yeah. Yeah, everyone's dealing with it, I guess. I wasn't feeling great before this too, and then I got a cold, so it just kind of compounded it. But yeah. So these could be anything they want, really, but in this, usually we'll be dealing with power series where the coefficients have something to do with the derivatives of a function. Usually they're these Taylor coefficients. I don't know why I'm circling everything. Right, or we could plug in some other point here besides 0, and we could do a Taylor expansion around some other point, right? That's not a problem either. The problem is, in the real case, that sometimes you can have infinitely differentiable functions and they have a Taylor series, but the Taylor series doesn't actually equal the function at any point besides, at the point that you expand around, it has to be equal at that point. But I'll give you an example in a second, which is the function piecewise defined. And so this is a real function. F of x is e to the negative 1 over x squared if x is not equal to 0, and it's 0 if x is equal to 0. Then in the book they show that all the derivatives at 0 are just 0. So if you were trying to expand this as a Taylor series, you would think it would just be like 0 plus 0x plus 0x squared, etc. But this is just the 0 function, right? So these two are not equal to each other, and that's sort of like an issue. In the real case, it seems like it would be nice if every function we could just expand it, you know, at some point, and there was some Taylor series, and it actually equaled the Taylor series in some open neighborhood of that point. But in this case, there's no open neighborhood where it's equal to this function. It's just 0 everywhere, and somehow you know, there's just something weird going on in the real case. It's sort of like we're missing part of the story here. And because we're missing part of the story, it can sort of disobey this nice thing going on here, which in the complex case, you don't get this. So in the complex case, if you have a holomorphic function, you expand it with some Taylor series, it's always going to be equal on some open neighborhood. There's always some non-zero radius of convergence. For any holomorphic function, right? But this is not holomorphic at 0. You can see there's sort of like a singularity here, but the singularity in the real axis sort of like misses this blow up thing going on. Okay, so right, so that sort of summarizes like why the case in the complex case is so much more interesting than the real case. The real case, you sort of lose information when you go to the Taylor series. Like we basically forgot about this entire part of the function here, and we just saw the entire function just looked like zero. Right. So then this is 3.3. And this is specifically talking about the power series expansion for a holomorphic function. Right, and this first theorem actually says, if we have a holomorphic function on an open set and I pick a point, then there actually is a Taylor series and it actually does converge to the function, at least in some positive radius of convergence. I've been dealing with something for a couple days. A drink of coffee. Yeah. I forgot to get a water. I was gonna get a water. Yeah, coffee's good for me in the morning, but towards this afternoon I get a little jittery or something. I don't know. Okay, yeah, so let's look at this theorem. This theorem basically just guarantees that this Taylor series actually does converge to the function. So we don't get weird pathological examples like the one like that function in the real case that sort of has a blow up at a point, but you don't see it in the real axis, right? So this says that that's not possible in the complex case. So let U be in C again, some open set. Anytime you see a U, it should be just some open set. And let F be holomorphic on U again. So write it like that. Holomorphic on U. And now again, we're going to let some P be in U. So pick any point in the open set. You think of your open set looks something like this. We're just picking a point here, P. P in U, and suppose that there exists some R greater than 0 and some D, so some disk around the point of radius R, so just some small disk around this point. And let's say that this whole disk is contained in U. Then the complex power series which is basically just the Taylor series around this point. So the kth derivative of F at P divided by K factorial. That's just your Taylor coefficient times Z minus P to the K. And of course, K is going from 0 to infinity in the sum. Then the theorem says as long as this disk is actually contained within U, so meaning that it's holomorphic on this entire disk, then this Taylor series actually converges and it equals to F of Z for every point inside this disk. So for every Z in this disk of around P of radius R. So it's actually two statements, that the function actually equals the Taylor series and it converges for every point. So really two statements. So converges, and the second statement is that it actually equals F of Z. Okay, and we just showed a counterexample in the real case where you had a function that was actually C infinity, it was infinitely differentiable at every point, but it had a Taylor series that it wasn't equal to on any open set around zero, because every open set around zero, the function was just zero, and we had a non-zero function. So, I think I have to make a phone call, guys, so I'm gonna end it early today. Also, of course, I don't feel good, but I will be back on Saturday. I'm gonna talk about a little bit of research, and maybe possibly Friday or next Tuesday as well. I'll be back, and we'll just keep talking about holomorphic functions. I think I'm gonna get into like some Cauchy estimate stuff. So we're gonna use the Cauchy integral formula and the fact that we can write every function as this integral, to be able to get estimates for holomorphic functions. And then eventually we'll be able to prove Liouville's theorem, which says if a holomorphic function, which is entire, that's defined on the whole complex plane, if it's bounded, then it must be constant. So Liouville's theorem is important for proving, I think, the fundamental theorem of algebra, and it's just nice to have in general. So as you can see, these holomorphic functions are very well behaved. They follow this Cauchy integral formula, so you can get nice estimates on them because the value of every at every point is some integral, and you can estimate that integral. So very, very nice results in complex analysis, and like I've said before, it's one of my favorite subjects to teach and to go over. So yeah, let me try to raid someone here real quick, and yeah, sorry for the short stream, but I will be back shortly this week.